G'day everybody and welcome back to the channel. So today I'm gonna sort this out. I've got a bit of a problem, but I know what's going on. I've just left the other night to go to bed and haven't come back in here yet until now. Alright, so I'm gonna just power this up. I've got the output disconnected from this part of the circuit. If you look at these wires, they're actually just the next track to where the ends of these 100 ohm resistors are. I've just got a 15k resistor in here going to ground on this side of the input pair and 15k to ground on the other side for now. We're just going to take some measurements in reference to ground. I just want to see what's going on with these two sides. I've got a funny feeling that one side's hitting the rail. There's some sort of imbalance problem here. So I don't know if I've got a bad transistor in here, if I just need to add some offset in the bottom where these two resistors are. The reason why I'm a little bit confused is because I actually had this perfectly trimmed out before. I had a 56k in one side and a 68 in the other. And then when I went to the Wilson current mirror, it evened out better and I had a 68k in both sides. Anyway, when I hooked back up to the output stage, I lost my gain. So I took the Wilson current mirror back out and now I have offset again. But when I put my 56 ohm resistor back in here, the offset didn't go away. So something's up with this circuit and I've got to figure that out before I can hook the output up, because the output's just going to get pulled to one of the rails or somewhere in between. So I'm just going to power up. Alright, we're powered up, we're not in current limit or anything. So right now I've just got a single differential pair in there with a long tail pair, whatever you want to call it, with a current mirror down the bottom, current source up the top, and there we go. Well, that change was sudden, I didn't even see that. Just going to warm up the opposite transistor, yeah. Alright, so that is what's going on. Interesting. Alright. The reason I'm confused as to what's going on here is because these transistors are all closely matched and this was working for ages. A day or two. Huh. No. For the record, I've got 15k to ground on each side. I always forget that meter's got a speed button, which I hate. 59. Alright, I'm going to go get a pot and play around with the offset on the bottom here. I've already tested the transistors, that's why this is here, and they tested good, but if you all remember, I had D822, 2SD822 and 2SB722 transistors in here, and now I have tip 41, tip 42. All my 722s were leaky. They test good on this. No, I'll just show you guys, it's actually quite interesting. If anyone's wondering, yes, this is from when I bought transistors off AliExpress a while ago. I got a whole load of D882s and B772s, and I'll just show you. So you see, it looks like it's a good transistor. VB 713 volt, 0.713, which is a bit high for 1 milliamp. 770 at 5. Okay, that's all right. VT sat 0.007. You'd think this is a good transistor, right? IC leak. There you go. 0.031 milliamps. I shit you not. I mean, you can see the pile there, and the rest of them are in the bin. I don't care. It cost me like, I don't know, a couple of dollars, like $1.16 for a huge pile of them. So it's not like I lost money, but yeah. Anyway, oddly enough, all the 822s are good and all the 722s are bad. So I threw the 722s out and ordered the new set from someone that I've got good parts from. Anyway, so although what I'm getting at is, although I've tested them, there could be some sort of problem. So, because some of those don't test with any leakage, but when you put them in circuit, as soon as you apply power, they just turn hard on, even with the base pulled to the emitter. So transistors can do funny things when they're faulty. So yeah. Anyway, I'm going to muck around with this circuit a little bit. I'm going to put a pot in the bottom here. Now what? Something else I want to see is how it reacts to a load. Just 100k, nothing steep. Oh, what am I doing? I'll bring ground over to this 100k resistor. Aha. Let's put our 68k back in. Sorry, I don't know why I keep saying 68k. I've got too many circuits in front of me. It's getting hard to remember all the bloody resistors. Minus 22. 460. Alright. I'm going to have to play around with collector and mainly tail resistor values and get this balanced out. I'll be back soon. Alright, this is getting weirder and weirder. I had a pot in there. I had close to 30 ohms on one side and 82 on the other, and it worked. And now I've gone back to resistors. I put the original 68 and 56 ohm that I had in there at the start, and it's just working again. I don't know what to make of this. I don't understand how the hell this can be working now with these values, and a minute later it needs different values, and then a minute later it's working like this again. I've even tried swapping the one transistor that I've still got a spare. Oh, sorry, it's this one that's closely matched to these ones in and out, and it's not making a difference. I want to hook my output stage up to this, but I can't do it obviously with this not balanced, because I'm just going to be slamming into rails. So, and no, it's not breadboard. As much as I hate breadboard, I mean, you can tell that there's nothing. I mean, that's me, obviously. Hold on. Oh, don't tell me. Don't tell me. Ah, man. You know how long I've been focusing down there? This is why I hate breadboard. Now, that's just because I warmed up a transistor with my finger. Oh. Yeah. I'd say that's just this guy I warmed up. Yeah. Alright. Let's see where this settles back to. I've still got 15k to ground on each side, so we should have a nice little ladder here, and we do. Alright, let's see if it sits here. I'm going to go have a cup of tea and leave this sitting for a bit, because I'm starting to lose my trust. You saw it before. It was down near 0.6 of a volt, then it was at 20, then it went back to 10, now it's back up to 30. I mean, this is ridiculous. The other thing that I've noticed that's really, really odd too is that yesterday, when I had a 56 ohm on one side and 68 on the other, it took 122 millivolts in to get 60 volts out, a swing, peak to peak. that is. And today it is taking a grand total of 28. Let me just say the 28 is the figure that it should be closer to, not 128. But still, I don't seem to get why this is happening to me. And again, now we seem to be about 2 volts too high. I'm not going to lie, I haven't played around with this sort of circuitry for a few years. The last time I played around with current mirrors and long tail pairs and all that sort of thing was when I was, it was the power supply that I'm building now, because I wanted to make it all transistor. I started with that goal, moved to op amps, and then went back to transistors because I realised I was being lazy. And so anyway, let's just see what this does. This is 68 ohms on each side again. If you're wondering my method to madness, why I've put that back, it's because I made a little movement up here and the voltage changed, and then I saw it sitting up 2 volts, so I thought I'd just go back and see. I might have to leave a pot down there. That's fine. That's fine. I'll bring the pot back in and then I'll get the rest of this circuitry ready to hook it up to the output stage. I just want to leave this sitting around where it should be at and see what happens for a little bit before I hook it up. Well, that's a good sign. So the other thing I've noticed that it was doing was, oh, actually, you know what? I'm an idiot. That was when it wasn't biased. No, don't worry. I thought I saw voltage change before, but that was when it was actually playing up and it was sitting down near the negative rail. And I put a feed in it and it biased itself. That's completely normal. So now it's not changing its bias with the signal, and the signal is coming out at about 55 volts for only 18 millivolts in. Let's go up a little bit. Alright, we're clipping on the top half there. Look, that's 57.6, and as you can see, there's offset there that I could trim out. If I brought that down to 30, that wouldn't be clipping there, and I could turn that up to the 24 millivolts or whatever it was that I had before. It's on 19 now. So, okay, I'm happy with this. I'm just going to leave this. Well, you know what? Let's take the signal off for a second. And let's just trim out this offset with a resistor. I should be able to get it close to 30. I hope I'm not boring anyone doing this on camera. I just thought these circuits are, tricky for people who are just getting into electronics, just starting. And I thought I'd just catch some of the nuances of it on camera so that other people feel better when it happens to them. No, I'm being funny. Honestly, just so that you can learn. I might want to put a bit more than 10k there. I can't win. This is exactly what I'm talking about. I've only had this sitting in the breadboard for a day and everything's already oxidized. It's just, man, I hate breadboard. You wonder why. Alright, let's stick our signal in and see how linear that is. Oh, God. Okay, that was just my finger. Turning up. That was just my function generator. So we've got 61.6 volts there, and it's not the store. Well, I mean, it's just, but it's pretty symmetrical. There's 60 volts. 60.4. Let's back that down. We'll go back up a bit. There you go, 60.4 volts, 60 volts. That's at 20 millivolts peak to peak in, 60 out. Alright, I'm going to leave this sitting here and have a cup of tea and come back and see if it's changed. If it hasn't changed, I will trim this off and get it completely balanced and then start hooking up the output stage. I just want to say before I go off and leave this sitting here, which it's only been here for an additional minute already and it's doing better, not worse, which is good. I have decided I am definitely going to match up sets and change these. Look, in view of the fact that I've got a diode string that I want to run 2 milliamps through, these transistors have got a bit of heavy lifting to do. These are rated for, I can't remember, but more than them. I mean, these do, they do handle quite a bit of power compared to some TO92 devices, but these handle more. And the thing is, I've already built this amp years ago. It didn't have a proper input stage. It just had a very crude Class A amp driving it. But everything that I've built so far on board was made and working, taking a signal, making, rated power and all that. And I had these transistors in it. So I know these will do the job. So I'm going to use them because that's how I originally designed the output stage, and I just think it's going to benefit from it. I don't think it's even going to have enough gain. Well, I mean, it might have enough gain, but I can see these little MPSA 92s and 42s running quite warm, maybe even hot, which that is not something that we like to do or should do. I just was thinking about something. I'm going to take my fingers, because they're both the same temperature, and I'm going to warm up both at the same time down here in the current mirror. Alright, now let's try the top two and the bottom two. Now, I'm touching resistors, shorting stuff out with my fingers, so just wait until I let go. I reckon what I really need to do is get thermally coupled transistors going here. I mean, that's what I'm going to do in the build anyway. I'm just going to glue these together. I'm not going to order some yet just for this amp, but maybe I should have done that on breadboard. The thing is, with this sort of design, your input stage severely affects the offset coming out the output, which is why in my original design I didn't do it like this, but I want lower THD, I want super low THD. My amp that I designed has ridiculously low THD, but the input section I was using with it did not. And I just think that's a waste of a really good amp. Alright, I'll be back soon. Alright, I've left that powered up for a while and it stayed stable, so I've gone and hooked the output stage back up, and I finally am having luck. We're not pegged to a rail. We've still got severe offset because this isn't trimmed out with a pot or anything. The transistors aren't thermally coupled or matched, but it's the offset you'd expect for mismatch. Actually, let me go get the power supply turned on first. That might help just a little bit. There you go, 60 millivolts offset. Now I'm not so concerned about that. I can start trying to work out why I've got no gain. I've got a funny feeling that these devices, I'm going to have to put a bigger device in there that can handle more current, because, well, I've noticed with the offset this device get a little bit warm. When I null it out, it spreads between the two, but I still don't think my drivers should be getting warm. Unless this cannot handle the current and it's losing its gain. It's the only thing I can think of. Okay, there are other reasons that could be happening too. That's what I'm about to investigate now. I was up to this the other day, but then I hooked up my output stage and everything just peaked towards the rail, so I had to resolve that problem first, and it seems that I have resolved that problem. So on to the VAS again. So actually, you know what, I'm going to put the Wilson current mirror back in, because since I have resolved this problem, I want to see if I still have it with the Wilson current mirror. Let's do that. Anyone wonders why I'm doing this, it's because these ones are matched. This one I'm putting back in is not matched. That will not work. I'm sure it'll do something, but it won't work. Just make sure all my connections are correct. That looks like a Wilson current mirror to me. Alright, let's see what we've got now. Hey, that's actually quite promising. I think this time we're up and running. Ah, blimey. Hoping too soon, hey? Alright, let me investigate what's causing this. There's got to be a reason for this. Maybe I'm missing some circuitry. Maybe I need to do something to compensate for the extra volt drop of the transistors going to a 4 transistor Wilson current mirror. I'm not too sure. I've only ever played around with pretty simple front ends, so I've got a little bit of learning to do here, I won't lie. Alright, I hope everyone got a good laugh out of that. I did. Because I left the lab and I came back in and I put this meter here. I hooked on to ground and I hit the power supply and went to have a look at voltages, and I realized something immediately. For starters, the drive that goes to the Darlington stage, VAS, is in the wrong side. So let's move that over to this side. Actually, now that that's a current mirror, wouldn't I have a 4 transistor current mirror? I'm going to have, I think I've just answered 2 questions here. Not only I was taking the output from the wrong side, but I'm going to have to add another transistor to the mix because I'm going to have almost minus rail voltage now, I think. Let me just ground this again. Alright, let's have a quick look at voltages. Because as I was saying before, if this gets too overcomplicated, I won't do it because I'm not a fan of putting too many things in the signal path. Yeah, that's sitting on the rail as you'd expect. Everything down here will be now, won't it? Alright. I come to the conclusion that I have got this biased wrong in some way. So either up the top, the source, or this mirror down the bottom is doing something that's not helping me. Let's just have a look at ground. Actually, let's start at negative and just go up and see what we've got. Yeah, this is not biased upright. Alright, I've got to work out what I need to change with the Wilson mirror, because there's something I'm missing here. Because it's acting as a diode on each side, I've essentially I've lost my bias setup. I've got to work this out. I know I'm missing something really, really simple, but yeah, I haven't really played around with Wilson mirrors before, so I should probably have a look into that. Boy, am I glad I did this off camera, because I would have wasted so much of your time. Ah, God. This is just what I'm like when I don't play around with certain circuit topology for a while and then I come back to it. I'm sure it's like that for everyone. You know what? The deeper you get into electronics, the harder it gets to remember everything, because you only have to remember so many more different circuit topologies. And the more you work on one area of stuff, the more you forget something else. And then when you go back to that, you've got to start picking back up on that. Anyway, this is actually only 1.3 volts off the rail. And I just put a pot in there to trim the bottom, but I don't think that's something that you can do with a Wilson current mirror. Or at least when I tried it, it didn't seem to have any effect. Now, I'm not sure if that's because my resistor value is too low or not, but it certainly didn't have any effect. Huh. Oh, I know what I did. I had that going to ground, not the bottom rail. Whoops. Whoopsie indeed. Yeah, okay. I do need to investigate this a little bit. Alright, well look, I'll be the first to admit it when I'm wrong. I know I'm wrong here. I don't know all the math, and I understand how a 4-transistor Wilson current mirror works. I mean, obviously I understand how it works to a degree, but I have to work out how to bias it using current mirrors and current sources, not traditional biasing methods, you know, with a resistor network between the rails going into the bases. That's where I'm struggling with this. I find it really easy to bias using current sources, a long tail pair, but as soon as I make this current mirror into a Wilson current mirror, there's something I've got to learn here that I'm missing. So I'll work that out now off camera, and then I'll come back, and then hopefully I'll be able to make this all work together. Alright, we're in Doug Self's 6th edition power amplifier design handbook. That's what I started with. I never went to one of these designs. I just went straight to this. And I've just inspected the connections, and it's definitely set up exactly the same as how I've set it up. My two bases are tied together and tied to this rail. Maybe I'm taking my output from the wrong place. I'm going to have to do a little bit more research, but I will definitely show my working out on this, just in case anyone else is trying to do this. It may help you as well. Oh man, am I having a slow day today. You know, it hit me as soon as I put a signal through it, and I stuck a couple 100 ohm resistors in the bottom here and started shunting them with smaller values. And as soon as I made the left one smaller, I saw my signal get better. So I looked at the DC, and the DC started coming back to where it should be. And then I realized something. Because everything's now swapped over, instead of this side having the 56 ohm resistor and this side having the 68 ohm resistor, it needs to be the other way around. Let's just get my multimeter over here and verify that that's actually what's going on, but I think it is. I think I've just made a really stupid move and forgotten something. Let's see. So we'll have a look from the 0 volt rail. We'll have a look at our collector of our long tail pair. You know, I'm just going to get a piece of wire in here. that is the collector. I'm just going off where it goes into the emitter of the into the collector of the NPN from the current mirror. So can you all see that? No, yeah, you can. 59 volts. If I just take this 56 ohm resistor and put it across this 100, yeah, pretty obvious what's going on here. Alright, let's put 68 and 56 back in first. I doubt that's going to work. I think I'm going to need a slightly bigger resistance on both sides now, but there's no harm in trying, is there? I would have thought there would have been a little bit of a difference. Maybe not. Let's put 100 back over here, because like I say, I think I need more resistance. Aha. That's interesting. Quite interesting. I'll play around with these resistor values off camera. I'll stick a pod in here. Or maybe I'll go get a couple of, say, 500 ohm pots or something, and I'll work out my optimum resistor values, and then I'll come back and show you what I've got. But it's pretty obvious what's going on here. So I feel like a bit of an idiot, but at least I've shown what the problem is, because I'm sure someone out there is going to have the same problem. I mean, especially if you haven't done this before. I've done this before and I've just forgotten that, you know, I can't imagine learning it. Actually, yeah, I can, because I remember the first time I built a long tail pair with a current source at the bottom, and it was a 3 transistor current source. And let me tell you, that was for a current sensing application, like sensing a voltage drop across a very low resistance shunt. I had to build super transistors on the input, and I had to have very high impedance in the whole network to get the gain that I needed. That was pretty hard to pull off, considering it was the first time I played with one. So if I can help anyone with this, you know, that's what I want to do. Furthermore, what I'll do, once I've got this worked out, I'll draw it out all on paper and explain it a little bit better to you guys from the paper. Alright, let me go work out what should be down here, and then we'll pick up from there. So it looks like I am going to be able to pull this off, which is good. Good for me. Alright, something's just come to my attention that I probably should have mentioned about 10 or 15 minutes ago, but I'm going to mention it now. Before, I was having trouble with the Wilson current mirror, the 4 transistor current mirror, because I had, well, forgotten to swap the sides around. I was having a problem which seemed like it was matching or thermal mismatch between either the current mirror or the long tail pair. Turns out it was the breadboard. You might have noticed on video I touched something over here and everything changed. Well, off camera I ended up cleaning out that area of the breadboard. What had happened, or this is what I think's happened, it could have just been oxidation, but I've got a lazy habit of pulling the little pieces of cardboard, you know, when you get parts brand new, and let me just grab something for example. Alright, you know our resistors have this on each end too. Well, I just pull them out, I don't cut them, and that leaves a little bit of sticky residue on the pins. And then when you slide them in and out of breadboard, you guessed it, the residue ends up in the breadboard. Don't be like me, don't be lazy. I just wanted to pop up and add that into the video because I feel it might save people time that are breadboarding stuff. Just that one simple tip, just cut everything out the strips. You will have, you know, slightly shorter legs to work with, so It's up to you, but I just wanted to mention that. Okay, so I put two 500 ohm pots in here. Now I've only got one end of the track and the wiper hooked up, so if I open it all the way that way, it's 500 ohms. If it's all the way this way, it's 0 ohms. Now, if I wind them down closer to 0 so that they're both the same, and then try and adjust the offset, it's impossible. I get that that's because I'm running out of usable track, but ratio, sorry, you know what I mean. But here's the thing. At the moment, I've got one of them set at 200 ohms. The other one's set at 175. And that's the best I can obtain. I don't know what's going on here. Look, up until now, when I've said I'm going to go do some research on this, all I've done is look at that. Look at this picture up here and look at a couple of amplifier designs just to make sure that we are indeed taking the signal from... Oh no, this is something else I was looking at. Same publication. Let's just go back up a little bit. So I had a look at some schematics just to make sure that we are taking the signal off of here, and we are. But now I think I am going to have to go and do a little bit of research into the 4 transistor Wilson current mirror, because it seems to me I'm still running 2 milliamps down here. That's obtained with two 5.6k resistors in between VCC and a capacitor between the center point of the resistors and VCC positive, and ground, and the LED is in between VCC and the top resistor, and that node there goes to the base of that transistor as a reference. It's got 680 ohms in its collector, and in its emitter, and then 200 ohm resistors going over to the long tail pair, which has got, providing both sides are biased equally, 1 milliamp in each leg. And down the bottom here, whether I've got resistances that are closer to 47 ohm on each side or closer to 250 or 500 ohm on each side. Sorry, I said 250 and 175, didn't I? No, these are close to 500 ohms now. But anyway, what I'm getting at is I'm missing something. It seems, I did this to improve linearity and reduce offset. And it seems to me all it's done is create offset. So I don't know what to say about that. That's quite interesting. I'm going to have to do something to rectify this. What? I'm not sure of yet. Like I say, I've got to go actually do some research now because, yeah, it's got me. I'll just show you what's happening. The smallest little change of the pot, and I mean small. I've got steady hands when it comes to adjusting pots and stuff like that. And now it's making me a liar of myself. Come on. I could not get that anywhere near that before. Maybe I had crap in my breadboard. That does happen. Let's just see where this settles out to now. I still don't agree with this. I mean, that does not ring stability in any way. You know what I meant to say. That is unstable as hell. Quite interesting. I'll try and adjust this other side because we're up closer to 500 ohms, I've got a little bit more to play with. See, I just touched that and it changed. You couldn't build an amplifier like this. I get it's not a built breadboard, but still, I mean, this is unstable as. Alright, I'm going to have to go and do some research on this because this is just ridiculous. If you try and turn this pot like, you know, even just slowly, it's that sensitive. You know? Way too sensitive. Anyway, I'm going to have to go do a bit of research on these 4 transistor Wilson current mirrors, even the 2 transistor current mirror, because, well, this is only an enhanced version of that. So, I mean, the way I see it is this is just, I'm seeing the effects of 2 times what I would see with just 2 transistors. I hope that makes sense. But I just don't see that working out very well in an audio amplifier. The thing that confuses me is yesterday I did a bit of reading on it, on using a Wilson current mirror in an audio amplifier, not the circuitry behind it, like how to implement it. I mean, people that were doing tests with their audio analyzers to see if there was an improvement in THD or anything like that. And people said what I thought, that it improved offset, but someone said that there was a small increase in THD. Now, I just thought that, you know, that was probably because someone did their layout wrong, you know. I don't mean like the layout of the traces, but I mean resistor values, stuff like that, you know, their circuit choice. But after seeing this, I'm starting to wonder, because that would be terrible. Alright, having a look at this document here from Analog Devices, Chapter 11, the current mirror, and I scrolled down to the appropriate section. Excuse me again. Alright, here we are. What have I done? Don't tell me I've loaded the wrong document up. What? I was just looking at this, but there was a resistor added. Hang on. Let me see what I've done. I'm sorry, my bad. I completely went past it. So, alright, we've got this bit here which talks about our emitter degeneration resistors. But if we scroll down a little bit further, we see this extra resistor here added to the base of Q1 to compensate for the finite beta of Q2. So, cool, we've got the math for this too and an explanation. Alright, so I'm going to have a little bit of a look at this and see if this has got anything to do with what is going on my breadboard, and we'll have a look and see what that does. Alright, I'm back in here. I actually was going to go to bed before, not just because of the time, but because I was in a lot of pain. I've got a injury on my right shoulder, but it causes knotted muscles all over the top half of my back, and it's a real problem sometimes. Anyway, it's settled down, so I want to just get this little section finished before I give up for the night. Anyway, I was reading this and I was thinking that adding this resistor here might only help, for example, let me scroll down a bit more here. where it's buffered, or where's the first Wilson one with 3 transistors? There it is. Or here, where you've got the Wilson current mirror, but you've got one that's diode connected and one that's not. So I was thinking maybe putting it here might help, but I'm not too sure. But then when I came down here, here it is. It says adding a 4th transistor, what I've done, to the simple Wilson current mirror in figure 11.10, we have the modified or improved Wilson mirror. Wait, what? That didn't sound right. The improved input-output current accuracy is accomplished by equalizing the collector voltages of Q1 and Q2 at 1 volt base emitter. This leaves the finite beta and voltage differences of each of Q1 and Q2 as the remaining unbalancing influences in the mirror. Now, if that leaves the finite beta and voltage differences, let's just forget the voltage differences for a sec. If that does leave the finite beta differences of Q1 and Q2, well, let's come back up here. Sorry, down here. Well, that's exactly what I was thinking. Well, actually, no, I was thinking Q1 and Q3. So, you know what? Maybe it's something that I'm going to have to do in both legs. When I say both legs, I'm going to have to go back up to here to explain what I mean. So, where we've got just one current mirror, we have a resistor on the diode connected transistor. I'm thinking, if we come back down, my apologies, to this, if we add a resistor here and here. So yeah, on Q1 and Q3. I was right, sorry. I confused myself too much, I know. Now, how do we work the value of that resistor out, you may ask? Let's go back up here. A lot of upsies, downsies. My apologies. Well, there's the math for it. So, RB equals beta plus 1 divided by beta. I'm not going to read all this out to you. You can see the formula there. And also, we have an example here. Examples are always very helpful, especially if you're like me and you're bad at math, because sometimes with electronics, you only need to be in the ballpark, and then you can dial it in to perfection once you have the circuit running. I'll give you an example of that. Emitter degen resistors. You can start with something like 100 ohms and then trim them both down, and then start trimming one more than another, you know, and work out what your value needs to be without doing any math whatsoever. So always read everything in these documents, guys, because you'll be quite surprised. A little bit more reading may end up saving you quite a bit of time. Not that it's not a good thing to learn the math for it anyway. I'm not saying to rush everything. I'm just saying, you know, these little explanations can be quite helpful sometimes. So it says here, for example, using A equals 2, a mirror gain of 2, in equals 1 milliamp, so RE emitter equals 26 ohms, and R emitter 1 equals 500 ohms, introducing about 500 millivolts of degeneration. RB should be 1578 ohms if beta is enough larger than A, so that that factor can be ignored, or 1626 ohms if it is included and beta is 100. So I'm just reading this last bit and trying to get my head around the last bit of this. So this only really works in high gain transistors, or where the transistor is actually set up so that it has high gain, because obviously your circuit affects the gain too, not just the transistor. In this situation, we've got high gain transistors and they're set up in a high gain circuit. So this should benefit us. Now, let me just work out what they're referring to by a couple of different things, like what A is referring to, and then we'll continue discussing this. Alright, I'm not too sure I've got this right, but I think A is referring to a mirror gain of 2 in this case. I'm not too sure. I was looking up here and I couldn't find anything else, but there is an A on this junction here, but it's not referring to beta, obviously, because we're just using beta symbol for beta. So, I wish I knew. Well, if A equals 2, a mirror gain of 2, A must mean a mirror gain of some value. So, let me get this to sink into my head, and then we'll come back over here and we'll give it a go and we'll see what it does. I've done a bit of thinking about this because, as I said yesterday, I was reading some articles, DIY audio threads and all that sort of stuff, Douglas Self, all those sorts of places, Rod Elliott. Anyway, and I've actually, not too many people, but 1 or 2 people I did notice saying that, like I said, THD went up very slightly when using the Wilson current mirror. And a few other people said that the offset was halved and linearity was increased. Now, I'm having a hard time believing the offset was halved because, well, as you've seen, I'm getting more offset here. So let's stick these resistors in. I'll work out at least a ballpark value, stick said ballpark value in. We'll see if it does anything to help us. If it doesn't, these 2 transistors that I've re-added will come back out and we'll just continue building it following the traditional blameless topology. That's kind of, I mean, it's pretty similar to that. Let me show you a couple more schematics too, because that will help. I'll just take these up to the computer. I've been having a good look. Sorry, I should do that a little bit slower. I've been having a good look. What's this? Okay, the reason I was looking at this is someone else's work, you know, a DIYer. The reason I was looking at this is because this is diode biased. And I just wanted to see if people have used this sort of topology that I'm using in an amp like this, if they had to add, you know, heaps of extra gain stages or whatnot. Now, this hasn't proved to be too helpful because, as we can see, this is not exactly what I would call a well-built, powerful amplifier. This looks more like something that's just been knocked up for simulation, but I'm not too sure. This might just be a simplified output stage and there's actually more to it. I don't know, but it's still only a driver and an output stage, so this leg here has to source a fair bit of drive to swing that. So anyway, that's why I was looking at that. What else have we got up here? That's just a random schematic I was looking at. Oh, I remember why I was looking at this. This has got some interesting cascaded input sections, and I found that of interest. As I showed you guys probably a video or 2 ago, I'm looking at building an input section very similar to this quite soon. So that's why I've been getting some different schematics from amplifiers with this topology, because I want to have a look at it and see what people have done. Here's another one. I've got a funny feeling that someone's copying someone here. Anyway, this has been on my computer for quite some time, but I was just looking at this because this is, well, for starters, this isn't Yamaha. I don't know why it says Yamaha, but anyway, this is done, you know, a lot more simple. So this is a more old school way of doing it. I don't know so much. It is old, but it's also quite simple too. I don't really agree going this simple. I believe in having a higher level of regulation, like I mentioned before about separate references and at least a current mirror down the bottom here. You know, at least that I agree with. So this is a little bit too bare bones for me, but I still like having a look at different things, and that I was just using for a demonstration. All right, never ever go to these websites and use their schematics, because I can guarantee you they will not perform well, if at all. I don't even know if these guys build these circuits or if these are just running simulation, but again, you know, it's always cool to have a look at as many different designs as you can. I mean, obviously, providing you understand how amplifiers work and you can read schematics. If you can't do that, then you're just going to be staring at it confused. But, you know, there is literally a million different ways doing this. You know, it's, what's the expression? A million different ways to skin a cat. Well, not that you'd ever do that. Don't skin cats, guys. You know, there's so many different ways of doing, especially front ends. You know, output stages, okay, you've got Darlingtons, you've got quasi complementaries, you've only got a couple of different output stages, a few, not many, you know, and then you've got how many different stacked up stages. What, you're going to have 3 stages, 4 stages, 5 stages. You don't have too many options there either. But once you get back to this front end, that's where you start seeing more complicated circuitry, and that's where you start seeing a lot of different designs. So it's good to have a look. Okay, there's not much going on there. That's actually been on the computer for quite a few videos now, because I was looking at the VAS section. Here's another one off of one of those DIY forum sort of websites. This looks a little bit more interesting to me, just the cascaded input. It's kind of, I kind of find it to be a good design in this leg, but I don't agree with a lot of the stuff that's going on over here. But there again, at the same time, I can see why they're doing that, because you're going to need a bit of drive to drive an output section like this. So again, you see what I'm saying about all different designs. There's so many different ways of doing it. It's always good to have a look. Here's another input section that doesn't use a differential pair. Alright, that's the mixer that I have to fix. That's just another bare bones schematic. Here's the Hummingbird amp. As you can see, the Hummingbird amp and my amp and this Blameless B amp all have a very similar topology in the front end. We all just have done things differently. Some people have implemented more protection circuitry, like clipping detection and clipping diodes and that sort of thing. Other people have implemented more clipping protection in the feedback and with a transistor to stop that from destroying itself or going into hard clipping, basically. Again, there is so many ways of doing the same thing, and there you go again with me. I'm doing a very similar thing, but again, we have differences. We have individual references. We've got a different output stage. We've got 2 driver sections. We've got a diode string instead of a VBE multiplier. We've currently got a 4 transistor Wilson current mirror, not a 2 or a 3. There's just so many different ways of doing things, and that's what makes this fun, because there's always different ways of doing things and there's always different transistors to try. So the amount of combinations that you can come up with between transistor types and circuit types, there's a lot of research to be done, especially for us DIYers, put it that way. I had to take a screenshot of this because I myself could not believe it. AI got it right for once. No, I mean, seriously, you'll probably know how many times you Google something and this bloody thing comes up with an explanation either about something completely different to what you've asked or it's just wrong. That's why you see my computer's full of so many publications and documents and data sheets. I just prefer to get my facts from the source, you know. But I typed in how does a current mirror have more than a gain of 1? Because 2, sorry, which I even I made a boo-boo there, which AI corrected me on. But you know what I meant. How does it do more than double what's replicate what's on the other side? And well, according to this, it doesn't, which is what I thought. But because the first transistor, this is where I'm amazed, it actually answered my question that I was trying to work out earlier. The second transistor mirrors the current of the first, we know that. But the first transistor also has a base current. Well, we know that, they both do. Even the diode connected one technically has some current flowing in its base to turn the junction on and make it a diode. But anyway, that's neither here nor there. Leading to a slight difference between the input and the output currents in a basic configuration. That gives me a massive hint. Because as we know from looking at this, I was saying, you know, I've got a funny feeling that this is going to help me in some way. And then I was trying to read this and I'm still confused about this using A equals 2, a mirror gain of 2. Does that just mean 1? I don't understand. Oh, because their emitter resistors are so different? The whole thing's lopsided? No, that still doesn't. I'm going to do a little bit more research before I do this. But this is what I mean about reading things, you know. I just read the whole thing. You know, I could have just stopped reading here as soon as I saw it just repeating what I already know. But I kept looking, and sure enough, I got a massive hint out of this because I didn't consider the base current, and that was very stupid of me. It's a current mirror. If, you know, there's a base current difference between one side to the other, of course it's going to be a poor mirror. So, yeah. Anyway, I'll continue working out this now. I've actually got an understanding of it. Now I've just got to work the math out. Now I've worked out what's going on. And then we can see if it actually works. I hope this helps someone. The whole reason I'm actually documenting this part of the circuit so thoroughly is because I just feel it's the part that's going to get most people into trouble. And especially when they hook it up to an output stage, I don't want people to, you know, smoke a whole pile of transistors. So I want to be very thorough on this. I also don't want to smoke my own transistors. Well, seeing as it answered that question so well, I just said, okay, how can a current mirror have a gain of 2? And it came back and said a current mirror can be designed to have a gain of 2 by using a specific transistor configuration. I'm not going to lie. By that point, I just scrolled down and then scrolled back up once I realized what it was saying. So let's just ignore that. I can explain this without having to read all that. If you add another transistor in parallel, basically, because they both have the same reference base voltage, but now they're sensing across the same resistor, they will both try and pull the same current, doubling the current in that leg. I hope that makes sense. It makes sense to me. However, that means that if we come back here, that example doesn't apply to us, but I can still make it apply to me. So let me just have a little think about this. Worst comes to worst, I can always do the math, but you know, if I can just stick a ballpark figure in there and play with it, because I mean, that's the thing, it's going to have to get adjusted anyway, so I don't need an exact value. I'm thinking, from what I'm reading and what I'm seeing here and here, I'm thinking, let's go stick a K in there and adjust that up and down and see what happens. But you know what, let's just go do that. We know it's going to be around there. I would think on the lower side, but like I said, let's have a look. And we know what the performance is like because I've still got this hooked up, so couple of 1K resistors. I'll just turn the power off. Not that I do that much, but sometimes you should. So I think I should be able to just remove these wires and replace them with the resistor. Yes, that's what I'm doing. I just wanted to have one more look at that diagram, make sure that I was inserting the resistor in the right path. Oh, no, I'm not. Hold on. So the side that's base connected, the side that's diode connected is not connected. Oh, the diode connection's taken after the resistor. Huh. I've got to wrap my head around that. How am I going to do that? Hold on. It's getting late, fellas. Let me think about this for a sec. Alright, so where this link is from base to collector, we're going to have to take that out on both sides, make it a little bit wider, put it back in the base but not the collector, and then take the wire that goes from the old transistor's base and put that to our new free node, and then we're going to take our resistor and connect our resistor between the collector and those two nodes. Yeah, that's right. I'll just pause the video and do the other one and make these fit so they're not going to touch. Alright, those resistors are in there. Sorry, I just need to lock my screen lock. Focus. Alright, let's power up and see what that does. That's 1K, by the way. Huh. Well, that's definitely changed things quite a lot, because now we're all the way back down at the negative rail again. Let's just make sure we don't have something connected wrong or loose. No. Alright, let's put these back in the middle. You know what? I think I've connected something up wrong, because it doesn't matter what I do with these. Oh, okay, let me turn the power off, just in case I'm frying a transistor's junction. I'll do this off camera, hold on. Oh man, this is just laughable. This resistor I had going from the two wires where they intercept to the collector. Don't know why I did that. Oh man. I tried laying this out, you know, not real neat, but spaced out so that you can sort of see kind of what's going on. And man, I wish I had have made this a lot neater, because it's just a tangled mess and it's very hard to get in here. And then on this side, I've taken a wire from the base instead of from the collector. So we just need to move that over one track and move the resistor over one track on one side. Alright, now we should be wired up correct. Let's see what we've got. Alright, that's more believable. And hey, oh no, I was going to say, you know what? That actually does seem to have helped. That is moving slower. And that didn't peg at the rail straight away. Although, you know what? It was turned off long enough that that's probably just because it's warming up. Let's see how much it needs. Oh, that makes it worse. Wow, that makes it much worse. Oh wait, I think I'm just turning this the wrong way. Sorry. Oh no, that's better. Wow, that's wonderful. There we go. So now I've got a much smoother control. Oh, yeah, it is smoother. It is smoother. You can see that I can pretty well dial a voltage in quite easily now. Oh, I don't want to lie. Hold on. This is slipping in that. Let me get something that's the right size, because I'm turning sometimes half a turn to get quarter of a turn, and the other time I'm turning a turn to get nothing. That didn't sound right, did it? Alright, let's put this in the middle. So that's about 250 ohms. Actually, let's put it 1/4. So we've got, I don't know, 75 ohms or 125 ohms. Somewhere around 100. And let's put this in the same spot and then just start adjusting. Oh, wow. Wow. Oh, wait, what? Oh, you know what I've done? I haven't given myself enough room for play. Alright, let's just go back to the center. That's 250 ohms on the right side. No, this is still too fiddly. Yeah, I don't like this. Wow, what? A minute ago I could, oh, we just had a loose wire. My bad. Okay. You know what I'm liking is the fact that these pots are both quite similar. You know how I had the other one turned a lot further before? Let's go back to emitter resistors. Just for a sec, let's see. That is interesting. 16 volts just sitting there. Let's go back to 68 and 68, and then we'll try 68 and 56. And I know I can increase my emitter resistance a lot more than this. I do know that. I'm trying not to do that. Let's put 56 in that side. I don't want to muck around too much either, because these are the only transistors I've got until more arrive in a week or so. So I've got to be careful with them. Now that's only 56 ohms. You see what I mean? How I don't need as much of a difference now in the bottom since adding those 1K resistors. But that's not helping me. That is not helping me. Because now it's even harder to trim it, and it would require even more precision of resistors. I'm going to go ahead and say that this is not a viable idea, and we're just going to go back to just a normal 2 transistor current mirror. Yeah. I'm definitely going to look into this and do experiments with this and get it to work for another amplifier build, or even for another preamp build that we can test in this amp or another amp. But for this particular amplifier, I'm going to call it quits, because I don't like what I'm seeing in terms of offset and linearity. It's really not good. My worry is that even if I included trimmers, say I put a resistor to ground for each. Oh crap, I've put that resistor in the wrong leg. Well, it's not much use even when it's in the correct leg. Yeah, even if I put, say a higher value resistor and then a pot across each one to trim it, which is what I'm going to do anyway, as I've drawn, I see this drifting more from where it's set than the original one over time. I guess we could breadboard 2 up, set them both, leave it and come back and have a look to test that theory, but again, I don't want to muck around that much for this particular amplifier build. Hey, my apologies about that, my phone just went flat. It's plugged in now, so that won't happen again. I think that's just stopped coming down. Actually, you know what? Let me keep talking, because I think my talking is warming it up. Hold on. That doesn't make sense. That would be warming all the transistors up. I'm blowing heat over everything because I don't want to just warm one up. Yeah, no, it's not a heat related thing. Well, here's the thing. As you saw before, with 68 ohms on one side and 56 on the other, we couldn't get this to work. So I would either have to use multiple resistors, trimmers, or go up into a higher tolerance resistor range. Now, with the 4 transistor Wilson current mirror and the 2 base resistors, this seems to be working a lot more with less differences in the resistance path at the bottom. However, it also seems that the changeover point of it, when I say changeover, I mean, say you set your bias here, and it slowly can go here or all the way down here. Oh, you can't see on camera, hold on. Say your bias points here, and it can drift all the way up here or all the way down here. What I mean is by changeover is how quickly does it snap to here or here. Now, with the 2 transistor current mirror, it seems to sort of do that. Hello? Are you helping? Well, I've been interrupted. I'm sorry, guys. I shall return soon. Hello. Oh, careful. Got 120 volts there. Do you want to say hello to YouTube? Say hello. Say hello to YouTubes. Hello. Oh, and the other one's in here. Alright, I'm going to have to get you down. Alright, I had to stop giving that cat attention because it was just asking for more. So, I've totally just gone off track here. Anyway, I've been thinking about this and I'm wondering, I'd like to get your opinion. I really want to get everyone's opinion on this. Would you like to see me, because I've got plenty of proto board. Let me just grab this box. This is why I want to do this, because it's not like I'd be wasting my supply. I've got a whole box of proto board here. So what I was thinking, and I don't need to, set up the whole thing with the current source. We can just take a diff pair and this current mirror setup, go over to the bench supply, build that up on a perf board, hook it up to the supply, set it at 2 milliamps, current limited, leave that running, and right next to it build another board up that's just got a 2 transistor current mirror with a long tail pair running at 1 or 2 milliamps. Leave both the boards running with the transistors thermally coupled to each other, and we monitor the drift, because this has actually got me more curious. I can't tell you how curious I am. I don't know, like I've just never thought about this and never thought that it would be that big of an issue. And so far from everything I've typed into Google, I'm not seeing anyone that's sort of looking at this area like I am, and I think this is probably a bit of a cause for concern in my mind, because, well, think about it like this. If your amplifier has more linear one day than another day, are your THD readings really accurate? I mean, the thing's got to be performing the same all the time. It must be stable. So I'd be very curious to see which circuit behaves better, the 4 transistor current mirror for what we're doing, or the 2 transistor one. Also, if anyone out there knows that I'm doing something wrong here, like, say the base resistors I put in are 10 times too large or 10 times too small, or, something like that, please leave that in the comments too, because like I said, I'm sort of going back to something I haven't played around with for a while, and I never played around with a 4 transistor current source anyway, so I'm curious. And like I said, I can't tell if I'm getting better performance here or with the other one. I guess we could put a signal through it and have a look and see what's got more distortion, but the thing is, I'm more concerned not just about distortion but about offset, because I mean, I don't want offset on my amplifier. So yeah, leave it in the comment section what your thoughts are on all of this, because I want to do this the best I can do it, and right now I'm not too happy about the way this circuit's performing. You know what, let's do this. Let's stick a resistor, a pot, across this 56 ohms so that we can lower it more or less, whichever way it needs to go. Might have to put the 68 ohm in there and stick the pot across it. Let's just do that. That way we can go higher or lower than 56 ohms, because I'm not sure which side of 56 ohms I need to be exactly, if that makes sense. North or south? Right. That's better than what it was without adjusting it. Alright. The other pot's not hooked up, that's just sitting there. So, oh god. Alright. That is quite close. Wow. I don't know how everyone works with breadboard. I'm seriously starting to think about just using proto board and soldering everything. The more I do this with more and more complicated circuits, the more it just shits me, for better of lack of a better term. And I think you can all see why. I'm sick of cleaning breadboards. Recutting wires, just, yeah. Anyway. Alright, let's try and adjust this. Wrong pot. Okay, I got to admit, having a pot across the resistor does offer, as I was saying before, a lot more ease of control. And I feel quite comfortable setting this where it needs to be set that way. Alright. That's still not right. Oh my god. I'll do it with a signal going through it because that's honestly the best way to do this. Because you can see that if you drive your signal up and up in voltage until it's clipping and then move this pot backwards and forwards, you'll see the clipping go more to one side or more to the bottom, and you can hone in and get it perfect that way. It's kind of hard to explain, but if you've done it, you know what I'm talking about. Alright, signals in. Why am I not seeing anything? We're off to a great start. Oh, my signal's not turned on, that's why. Right. Okay, I've got a negative clipping signal at 58.4 volts. Try and get that. Now bear in mind, I'm looking at my scope doing this, but I have the most linear signal I can obtain like that. Now obviously for doing comparisons, that's what I'm going to use. It's drifted off again. Yeah, I don't even think I'm going to need to ask for a vote on this one. I think the answer's kind of staring at me in the face here. This just is not stable by any stretch of the imagination. I would imagine even if I thermally coupled all this, they're already matched within a millivolt. I mean, yeah, you need to be more accurate than that for perfection here, but this is not even close to perfection. It's not even close to good. Alright, that's pretty linear again. Let me just turn the gain down because I'm still clipping on both sides. Alright. That's pretty some... Actually, you know what? Hey, I've just noticed something else about this. No, I'm taking this out of circuit. So, I'll have to... we're going to have to do a test on this now, but pay attention to this waveform. You see the tops are wider, and I don't mean that it's flattened off here from clipping, but I mean it looks like there's a sharper point here at the bottom. There is. Look at that. And just for reference, I noticed this yesterday without the base resistors in there. You know what we've got to do now? Let's go set this up with a single current mirror and see if we still have that. Because I can tell you now, that is terrible distortion. I mean, at this point, I'm not even ready to pull up an FFT. I can see it in the sine wave, and if I can see it in the sine wave, that is bad. I've got to take a phone call. Sorry. Alright, I've set this up again with just a single current mirror. pot to dial in one of the resistors. It's not perfect because it's fluctuating with the breadboard, thermal differences, VBE differences, gain differences. I've got a signal going through it. There's a bit going on here. Let me just, whilst looking at the scope, get this as linear as I can get it. Alright, that is looking good. So have a look at this. Symmetrical, yeah. Okay, it's starting to clip on the top. Let me just bring that back. That's just our offset. I can prove that because I can show you that way or that way. We can get it perfectly in the middle. You see we don't have that triangle-y looking wave on one side and, you know, sine on the other. We've got sine both sides. So I'm going to go ahead and rule this out. I'm going to say that the Wilson current mirror does not work, or a 4 transistor one at least. I'm going to say those people that saw extra THD were correct. They were damn correct. This certainly performs better like this. So I'm going to leave the video here because that is let me just get my pencil. That is this section developed. Now I need to work out the VAS. Now that's going to be done in the next video. What I'm going to do now is I'm just going to tweak these collector resistor values and make the appropriate changes to this drawing, and then I'll show you, because that will be that finalized. I may add some compensation to this stage too. I'm not too sure. From what I've seen, you can get away with doing your compensation just here with this layout, this particular layout that I've seen. I'm not 100% certain on that, so I won't have an answer for that obviously until the entire amplifier is built, but I will have an answer for the resistor values here in just a moment. Alright, I've decided, as you can see, we've got 60 volts peak to peak, and that is a nice looking sine wave. So this is what we're going to go with. This definitely works undeniably better than doing it the other way. So I've had a little bit of a think about the resistor values. I was going to actually lower the 200 ohm resistors to 82 ohms. But sorry, I was going to increase them. My bad, I'm not thinking too straight. I was going to increase them just a tad to maybe 120 or 150, but considering my rail voltage being so high, I'm thinking, if anything, I might want to decrease them to say 82 ohms. So with that in mind, I've just left them at 100. What I have changed is these pots here in order to offer a little bit more range, just to compensate for variations in transistors that people may use. I've changed the pot from 500R to 1K. So that'll work as long as your transistors are, you know, fairly matched. Oh, shoot. I've got to remove this. 1 minute. Okay, my apologies for that. So that is the final input stage that I'm going to be using. There may end up being an R and a C across here, but probably not. There may end up being a capacitor here to act as a bit of a noise filter. I don't like to use that, as I've discussed before. I like low resistances, high capacitances, you know, 15k to ground, and I don't like capacitance to ground unless I have to. So that comes at the last minute, you know, if it's needed. I'm just going to point this out just for people that are learning. I'm not trying to insult anyone, but if anyone's wondering why don't we put resistors in these two legs, the reason is because we've got a high impedance offered by these two transistors here, so that acts as the resistance. I know this also acts as a high impedance, but because it's only one node, we don't get any balancing. So this helps. Here, I forget what they're called, the collector resistors. I forget the term for it. And they do serve some other purposes too, but yeah. We're finally up to this now. So now in the next video, what I'll be doing is trying to work out if I can make this work the way I've drawn it on paper here, or will I need to either A, use different transistors here and more current, or maybe the same transistors with less current, or I might need to add an extra stage. I've got to work out what my problem is, why it's not working. I'm not going to lie, I don't even know yet, because I've been focusing on getting that right. So now that's right, I'm comfortable proceeding with the next area. I'll do that. So that's what we have for now. Alright, well, that's it for this video. So thanks everyone for watching, and if you got any comments, leave them below. Till next time, take care, and I'll see you all soon. Happy prototyping. Alright, I just realised something, and that's not right. I forgot to change a couple of things. So these 100 ohm resistors, I've had to play around with those, and well, I was going to actually make them a little bit bigger, but because my rail voltage is so high, I've decided to keep them at 100 ohm. And also the current that's flowing through here, there's a few reasons behind it, but anyway, the other thing I've done is I've added this little link in here that I had erased with the eraser and forgot to put back. But this is now, well, this area at least, what you see there will not be changing. I will just be adding stuff. So, oh, actually, no, I am forgetting something. So that resistor that I added in to the base, I wanted to have a look at that. I've completely forgotten about that. Let's do that. Alright. Hold on, why'd that go so dim? Stop. Oh, come on. I hate it when this happens. I don't have an explanation for this. My apologies. Alright, that's locked focus. I'm sorry. Okay, so I've still got this running. It's still where it was. Still got a nice sine wave. Actually, I will note that the sine wave does seem a little bit fat in certain areas, and thin in a few other areas. It's kind of hard to see. No, you can see that. You can see it's thicker in some areas than others, but that is way better than what we got with the 4 transistor Wilson current mirrors. So I'm still going with that, obviously. Let me just grab a 1K resistor, and I'll just power this off for a second. I mean, it's practically impossible to hurt the transistors here unless you, I don't know, put too much voltage, reverse space emitter or something, but still, I don't have any spares, so I should be careful, and I'm not a very careful person, as you can probably tell. Oh, I can't think. I'm going to have to get the document back up because I can't remember where that resistor goes. Jeez, that's not very good. It goes in between the base and the other transistor, and hold on, let me just do this before I get any more confused. So we're going to have to take this wire out and put that there, and the collector will move that wire too, if I can get the wire to behave for me. Come on, wire. Alright. No, not in the base, in the collector. Thank you. Thank you. Alright, let's stick our 1K in there and see if this has any What am I doing? No, that's not right. Hold on. Resistor from base. God. What have I done? Let me pause the video. Sorry. All I had to do was just put the resistor in there. As you can see, I didn't have to change anything. It was just confusing me looking at it. Alright. Let's power back up and have a look at DC conditions first. Okay, it seems to be coming back. We could have something a bit loose here too. That seems to be stabilizing a lot slower. That's all right. Well, we'll just wait. Oh no, that's actually going the other way now. I was just going to say I want to wait a little bit. I can see looking at the sine wave, and I'll just take you over before it clips anymore. We're still thin in spots and thick in other spots. It hasn't changed that, so that's not going to help us. So that can come back out. Yeah, I know I just said I should turn the power off. I really am a little bit too lazy sometimes. Alright, now that's got to stabilize again. So basically I have ruled those things out. Alright. Yeah, the sine wave is back to how it was. I'm just going to do one thing quickly and experiment. Why not? Because I want to finish this stage in this video, so even if it ends up being a really long video, it's still better to get it all done in the one video. Let's have a look at the effect of adding a snubber in here and see if that cleans up the waveform anymore. And I'll do you a favour and I'll show you the FFT. I don't need to look at the FFT so much yet because I'm pretty used to looking at a sine wave and I can tell different types of distortion just from looking at the wave. But for people learning and curious people, I'll show you on FFT. Let me just sort this out because my offset seems to have changed for some reason, which tells me that, yeah, breadboard. Let's get rid of that out the way. Okay. Oh. That's me touching the transistor, I think, not so much a loose connection. Yeah. This is why I'm always mentioning how body heat affects this so much. You'd be quite amazed. So that it was actually I must have bumped the pot. Oh. No. There you go. That is stabilized. Alright. Okay, that should be about 29.5 volts, not 30.1, but I mean it's close enough for me. Alright. Actually, should it be 30? I can't think if it should be 30 minus 1 VBE drop or if it should be 30. But either way, we're close enough. Bloody hell, I forgot what I was going to do now. Oh, snubber. Alright, I'll be back in a minute. Alright, I've grabbed a 100 ohm resistor and just to start with, we'll go with a lower resistance. And I've got a 10 nanofarad cap to start with. If I don't see any difference with that, I'll move up to say 100 nano. Obviously, I wouldn't, in the real world, move up in value that quick, but just to see if we see any actual difference on the scope, obviously that's sufficient enough. So that's our 100 ohm resistor hanging off the right collector. Now that's just killed my entire signal. Wow. This really doesn't have much power. Okay. Let's change the 100 ohm for 1K. Because 10 nano is quite small. 1K, where are you? 1K. I would imagine this will have quite a different effect with the rest of the amplifier on it, as it's in the collector path, which gets loaded down by the amplifier. So we will obviously come back to this later on, but I also like to see the effects of things whilst they are isolated to the circuit they're in. No, that swamps out the entire signal too. I'm still going to turn my input up and turn my scope up. I want to see, okay, I'm not near clipping. Let me play around with the input. Yeah, I can still turn my input up more and get the signal bigger again without being clipping. However, it's actually caused instability. So now we're just all over the shop. Actually, the more I turn it up, the more it masks that. Let me go back down to 22 millivolts. And that's what we have. So, yeah. Alright. I'll do one more thing. Let me put a 1 nanofarad cap in there. Alright, 1 nanofarad is in there. Okay, so that's not swamping our signal. I mean, obviously it's gonna have an effect on swamping, loading it down, depending on the RC constant of that network that I've put in. Oh, that's kind of interesting. Where's my gain turned up? My input turned up too much. Hold on. Let's have a look together. No, we're still... Oh, you know what? That actually does look more even, doesn't it? Huh. Okay, let's just take that capacitor out very carefully without disturbing anything else. I'm going to put the phone in the tripod because I think I'm seeing a very small difference, but I'm not entirely sure. Might have to open up the FFT. Alright. That's too far away to see, isn't it? Alright. So you can see that the waveform's thin, still a little bit more there and there, but it's thicker in the middle. I don't know, that could just be something to do with the scope. I don't think so, but I think that is the waveform. You guys watch. I'm going to tell you the second. I'm going to put one capacitor leg in, so I've just got to touch the other leg and I can say now. So it's out now. Now it's in. Now it's out. Now it's in. Hold on. Now it's out. Now it's in. I'll have a look in my own time. I'll play that video back and I'll have a look. And, you know, I'll see if I can see anything. I think what I'm going to do, I think this is the most prudent move. I think the wisest thing to do is just to leave a spot in my design to add these components later, so that we can still have a look once this is added to the rest of the amp. Alright, for those that are curious, that's what that looks like. I haven't read the manual for the scope yet. I don't know how to stretch FFT out anymore. Yeah, that does not look good, but honestly I'm not worried at all because I've got stuff going everywhere, wires going everywhere, grounds are not star grounds. Like the power supply, the cheap Chinese crappy one is ringing like a absolute, I'm not going to say it, I've had to swamp it down with capacitors. You know, I'm not surprised. Plus, it's only a crappy, cheap signal generator. I mean, it's all right. Let's have a look at the signal generator on the scope. Let's not do it like that. Let's put all this back. Just probe across it. Good enough. Okay, that's not going to work like that. Let me get a cable. So like I was saying, with the signal generator not loaded, just going through a bit of coax, it is set, the output is set to high impedance, but that literally means jack shit. I swear to God, it doesn't even make a difference. That's how it looks, without going into a 50 ohm load. So, I mean, need I really turn the FFT on? Not really. And I mean, those spikes were visible through my amplifier circuit. So like I said, I'm not worried about that whatsoever. I've probably got quite a good circuit here. Alright, well, that concludes the video now, finally. My apologies, but like I said, I wanted to include everything. I realised I was missing stuff. The schematic wasn't right. I promised an FFT and I didn't show that. So I hope that settles that. Alright, well, thanks for watching and I'll see you all next time.